Never mind the noise and the chatter. We are here for intelligent, fact-based conversation on the next episode of Bergen Banter. I am Dr. Larry Levanka, and I am your host of the official Bergen Community College podcast. So I have a question for you. Did you feel it? Well, what is the it? Well, the it in this case is an earthquake. And in our little corner of the world here in Paramus, New Jersey, we had an earthquake a little while ago that was centralized about a mile from where our campus sits. And that is not all that uncommon, in New Jersey at least, but we'll get to that. So we have Dr. Fred Marton here today, who is going to talk about some seismic activity and seismology and how that interacts with our world here in Bergen County. Welcome, Dr. Marton, to the program.
Happy to be here.
All right.
Thanks for having me.
No problem. So we had an earthquake in Paramus, New Jersey, but it was pretty small by seismic standards, right?
Yes.
So 2.4?
Yes, I believe it was a magnitude 2.4. A lot of people have some familiarity with the magnitude scale for earthquakes. They've read about it. They've seen it in their classrooms when they've had earth science in middle school or high school, et cetera. It's, as people may remember, it's a logarithmic scale. So as you go up, things increase by factors of 10. But it's a little more complicated when it comes to energy release for an earthquake. So when we talk about a magnitude 2 and a magnitude 3, a magnitude 4, the thing that's changing by a factor of 10 is the amount of shaking or the amplitude of the waves. So when an earthquake happens, waves are generated and they go through and over the earth and they literally shake the earth. Obviously, that's why we call it an earthquake. And we have instruments that will record these, seismometers. And you can measure the waves on the seismometer and see the amplitude, the size, how tall the waves are. And that was the original way that the magnitude scale was developed back in the 1930s by someone named Richter, which is often why it's called a Richter scale. We actually don't really use a Richter scale anymore. We use the numbers that are sort of developed from that because they become so familiar. But most of the time when an earthquake occurs and someone says, oh, and it measured whatever on the Richter scale, usually that's not technically correct. We're really using something else. For large earthquakes, it is actually something called a moment magnitude scale. But the numbers are basically the same kind of animal. So, but the thing about it is when it comes to energy, if we really want to talk about how strong the earthquake is, the energy doesn't scale with the magnitude number directly, but as a factor times that, if that makes any sense. So basically what happens if we increase the magnitude by a factor of 1, so we go from magnitude 2 to 3, 3 to 4, or we just had a 2.4 and then go to a 3.4, that's an increase of magnitude 1, the energy release goes up a little more than 30 times.
Wow. Okay.
And the reason I say about 30 times, it's actually because if you do the math, it comes out, if you increase the magnitude number by 2, it's an increase of 1,000 times. Wow. So we really are, by 1, it's the square root of 1,000, which is 31.6 something or other.
Got it. So it's not, so right, it's relative. By saying a 2.4, that doesn't mean that a 3.4 is just a little bit more intense. It's actually a lot more intense.
Well, by a factor of 1, it's about 30 times more energy. The earthquake that we had, it was a small magnitude, and actually it was quite, relatively speaking, a very small amount of energy. It's approximately the amount of energy you would find in an average lightning bolt. So, which of course is nothing to sneeze at. But by earthquake standards, it's quite small. The one that we had earlier in the year, which was a magnitude 4.8, the one that really got even people's attention up here, even though it was happening down more of a central area part of New Jersey. That would be about 4,000 times more powerful.
So with all of that power, obviously comes shaking and rattling and things falling. At what level do you start to get, let's say, nervous?
Well, again, it depends on a bunch of factors. Generally speaking, people I mean, if you obviously people notice this. I'm not aware of anybody claiming any damage to their property or anything falling on them or something like that. I guess if you had something on a shelf and it was very loose, it could have fallen or something like that. Usually, you need earthquakes starting to get up into the 4 to 5 range for significant shaking, for things to be noticeably moved around, falling, etc. In order for damage to structures, we usually go a bit higher. It's going to depend on, of course, the nature of the structure itself. So if you're in a house or an apartment, what is the building made out of? How is it constructed and all that? Of course, we're not in a high seismic risk area here. So the earthquake codes are not the same as you would have in, say, Southern California or Alaska, where they're prone to much larger earthquakes.
Yeah. So are there different types of earthquakes? Because I can say, just from my personal experience, I've been in a few now, very little ones. Some feel like they roll. Some feel like an impact, a sudden shot or a sudden drop of energy. So is that just in your mind, or are there actually different types of earthquakes that occur?
That stuff isn't so much because of the different types of earthquakes. If we really going to get into it, yes, there are different types of earthquakes. Obviously, there are different ones that have slightly different mechanisms and all that. There are type of earthquakes, for example, called a deep earthquake. They only occur at depths of 300 to 700 kilometers below the surface, and that's a completely different type of animal than what we typically see here. So generally, the difference that you're feeling is going to be probably because of one, what earthquake waves get to you, because there are 4 basic types of earthquake waves. And so which kind of waves are getting to you, because they'll move in different ways, and I can get into more details about that in a second. Obviously, the further away you are from the earthquake, the weaker it's going to feel, because as the energy moves out from the source, it radiates out. The energy sort of dies off a bit.
Dissipates.
It dissipates, and it's spreading out. So even if you don't lose energy, it's going out of a larger area. So therefore, it has to become less intense. It's like getting further away from a light. So the lights overhead, we move further away from them. The lights seem weaker, but it's still the same total amount of light. A lot will also depend upon if you're in a structure or something like that. Again, how it's constructed and how it might shake, because it may not move in one particular direction, but it'll move much more easily in another. So that could affect it. So when it comes to the earthquake waves, and that's the different types of waves will have different types of motions. So if we're going from one location to another, if an earthquake occurs, right, all the energy is released at pretty much the same time. If it actually is a very large earthquake, so if we're getting into those magnitude 7, 8, 9, then the energy release is sort of spread out over time, because it takes more time for the motion to occur. And as long as that is happening, energy will be released and all that. But let's, for the sake of argument, just say that all the energy is released at one go, like snapping your fingers. If that's the case, since all the energy is going out at once, all those waves start at the same time. But different waves travel differently and at different speeds. So if we're going from one location to another, there are 2 types of waves that travel through the interior of the Earth. Now, if you're very close to the earthquake, like you were when the Paramus one came, the waves are not going to travel very deep into the Earth, and they're so close to it that everything is going to come pretty much at once. There's not going to be much separation between them. But if we get far enough away, then the speed differences will allow the waves to sort of separate from each other. It's like if you and a friend get into a car and you start driving away from the college at the same time, and you are driving slower than your friend's going maybe 10 miles an hour faster than you. After a first mile or something like that, you're still relatively close to each other, but after 20 miles, 50 miles, whatever, the gap opens up. So that's what happens with earthquake waves. And so we have 2 types of waves that travel through the body of the Earth, through the interior of the Earth. We call them body waves, and specifically we call them S and P waves. The P waves are the fastest of the ones, and the S waves are slightly slower. And we call them P waves because they show up first. P stands for primary. S stands for secondary. So they're just named boringly for that type of stuff. And an S wave has a motion that's, if a wave is traveling in one direction, say from me to you, then I think I started to say S, but let me start with the P. The P wave, it pushes and pulls in the same direction. So you can also think of it as P for push. So it's going to kind of push up. So in other words, if you're standing on the ground and a P wave comes in, you'll get a little bit of a jolt upward or maybe a little drop down. But it's also going to be very little. P waves are typically not very large.
Okay.
The S waves are usually larger, and the S wave has sort of a side-to-side motion. Think like an S, or normally when you think of a wave, that kind of wiggly type of motion. And so that can cause motion, again, depending on how the wave comes in, it can move you backwards or forward, left to right, or whatever. The surface waves, instead of going through the interior of the Earth, you have waves that will go over the surface of the Earth. Those are even slower, but those are the ones with the biggest amplitudes. So they do the most shaking. And there are two types of those, and they have more fun names, more interesting names than P and S. The first one is called a love wave, named after a scientist by the name of Love. And that is very much like an S wave, but it's only doing that snaking back and forth horizontally. So only not doing any vertical motion, but back and forth, so left to right, or something like that as it comes towards you. So, and those people do report feeling those and report seeing those.
Oh, wow.
So if an earthquake occurs or something like that and they're looking in the right direction, sometimes they'll hear something, maybe they'll just be looking. People have reported seeing the ground go back and forth as it approaches them. And needless to say, sometimes it gets people very, very nervous or scared. The other type of one, which is slightly slower than the love wave, so it's going to be the last one to come in, is we call it a Rayleigh wave, named after, again, someone named Rayleigh. And that has the most complicated motion. It has a rolling motion. So if the wave is traveling, again, from me to you, as it goes forward towards you, the ground will, say, rise up, roll backwards, and then down again into the earth. And it does that as it goes towards you. So it's kind of doing a rolling backward as the whole thing rolls towards you.
So damage, I would imagine, can be subject to the waves, right?
Yes.
And
so
then after the fact, they can say this is what went through here and so on.
Right. So the surface waves are going to do the most damage. You
Right.
can get some damage due to those body waves, but again, they have the smallest magnitudes and they'll shake things the least. Those surface waves, they do the most shaking, have the largest amplitudes. And like I said, you have things going back and forth, up and down, forward and back.
Especially at those high energy releases, right?
The high energy ones, you can get a lot of them. And what's really amazing, and you may not necessarily feel it, especially if you're far away from the earthquake, but we talked about the seismographs, the instruments that record them. They'll record all these waves coming again and again. So the surface waves will sort of roll around the surface of the earth. They'll sort of go from the earthquake to where you are, pass you, and they can continue. They technically continue on around, and they can come around again. And really big earthquakes, very, very large earthquakes, we can see in the seismic record the packets of surface waves coming through again and again and again. It's really kind of cool.
Well, yeah, I mean, for a geologist.
For a geologist. On the other hand, if you're actually experiencing it at the time, you're not thinking, wow, this is amazing. You're going, what the heck is happening? Is my grandparents' China okay? And all that sort of stuff.
Do people still have China, by the way? I digress.
Some people do. Yeah, I guess they sort of do. Everyone, you have to eat off something. Maybe not fine china, but your dishes.
But all right, so back to New Jersey then.
Yes.
So we know that we're not like Southern California or Alaska, but we do have plenty of seismic activity because of some faults that we have that run through the northwestern part of the state?
Right. So every state will have earthquakes. There's no part of the country, there's no part of the world that does not experience some sort of seismic activity. Most seismic activity, most earthquakes are concentrated where what we call plates meet one another. The surface of the earth is broken up into a series of puzzle pieces, really, you can think, that fit together, that all move independently of one another. we call this idea and the study of this stuff plate tectonics. Sometimes it's called continental drift because it's the old version of it. But again, just like we don't really use Richter magnitudes anymore, we don't really subscribe to the ideas, the total ideas in continental drift. It's been expanded upon. But where these pieces of the outside layers of the Earth meet the plates at plate boundaries, that's where the most seismic action happens. So, for example, in Southern California, Los Angeles up to San Francisco, et cetera, you've got the San Andreas Fault, and that's where the North American plate meets the Pacific plate. Up in Alaska, you've got the Pacific plate, and it's meeting, again, the North American plate, and with slightly different motions, you get a lot of earthquakes there. We're not anywhere near a plate boundary here. The closest plate boundary is in the middle of the Atlantic Ocean, very far away from us. But you can still have earthquakes any place that, number one, has rocks, and more likely you have cracks or breaks in the rocks that we call faults. So a fault is a break in rocks along which motion can take place parallel to the break. So if you hold your hands together and slide your one hand up, down, left, right, or whatever, that's the kind of motion that happens along a fault. And the faults are not only at the plate boundaries, they're anywhere there rocks are. The Ramapo Fault, which is the one you were talking about, that is right here in the middle of Jersey. It actually runs almost 200 miles from Pennsylvania through New Jersey up into New York State. It's a pretty good sized fault system. And because it's a fault system, motion can take place along it. And when that happens, you can have earthquakes.
Is it the depth of the fault that can lead to larger earthquakes, or is it something else?
Not so much the depth. What's responsible for the larger of the earthquakes is the amount of stress that's accumulating and deforming the rocks in place. So
what is that stress?
So the stress. Well, stress is a measure. It depends on forces and applied to an area. So at a plate boundary where two plates meet each other, maybe they're trying to push towards each other, come together. That's what's happening, for example, up in Alaska. And so they're trying to push over one another, and so that's where those stresses are building up, because you're trying to push one thing past another, thing over another, and they don't like to move very smoothly. They'll kind of stick in places and all that sort of stuff.
And that's just the natural movement of the Earth. And that's
yes,
what
so the
happens
plates are all sort of doing that
Yes.
motion. Now that's where the whole plate itself is moving. So here in New Jersey, we're part of the North American plate, and we are moving very slowly away from, example, Europe at the rate of about an inch a year or so. But things don't necessarily move smoothly. Sometimes even if you push very far away on the edge of the plate, that push can be sort of transmitted or felt in the interior. So, like example, if you have a whole bunch of people lined up and someone pushes on the person in the back, bumps into the person in front. So it can sort of get transmitted through there. Yep. So the stresses that we have built up here in New Jersey ultimately are probably coming from the mid-Atlantic ridge in the middle of the Atlantic, because that's the closest plate boundary. So you push on the edge of the plate, and that pushes on the interior, et cetera, et cetera, et cetera. So that's where ultimately probably the stresses are coming from. You can have other things happening. Gravity can pull one thing down. You can have other geological forces that are within a plate pushing things up. There's a lot of stuff happening in the Earth, which is one of the reasons people love studying it and spending their time, just mapping things and investigating stuff. So at the fault, you have one side of it that wants to move in one direction, and the other side of the fault, the break in the rock, where the rocks want to move in another direction. And sometimes it moves slowly but steadily, and we actually call that fault creep. We got a lot of good terms in geology.
Sense. Yeah, it makes sense.
So it kind of creeps along. But sometimes it doesn't. It kind of sticks in place. And if that's happening, the pieces are still trying to move, and so therefore you're applying stress to it. It starts to deform a little bit, like if you were to take like a stick and start to bend it in your hands. It's bending. Scientists would call that strain. So it's getting strained, and eventually the thing snaps. And you release all that energy, and when it snaps, you get a release of that. I can do a quick little demonstration. one of my high-tech little demos things for people who are listening at home and not watching. This is just a tongue depressor.
Do I need to stick my tongue out, or we're not doing that? Okay,
No, you're not going to do
okay,
that.
Good. All
It's not sterilized, so you probably wouldn't want to do it
No,
anyway.
I hate the way those things taste.
Yes, so maybe you can make actually, you could get flavored ones because you'd have, ones from popsicles.
Yeah, right.
Anyhow, so if I take this in my hands and just, as I said, I'll describe it, and I bend it down on both sides, you can see how the stick is actually bending. It's a curve now, right?
Yeah.
So this is now strained, and I've stored energy in there.
Right.
I can release the energy very easily by letting go, and it snaps back, and I can actually do that on the table. And you hear that snap. That's a release of energy. And that's exactly the same thing as seismic energy. Seismic waves are sound waves transmitted through the earth. Now, we can't hear them. The frequency is all wrong, but that's the type of waves they are.
But to that point, you even feel a little bit of a ripple. When
Right,
do
you
that
could. If I
accidentally.
did that, you
Yeah.
would probably fit it. And in fact, if you put an instrument on here, like a seismometer, or
pick it up.
actually there are seismometer apps you can put on your phone. If you put that on the table and did that, it would record the wave. So, but the other thing that can happen instead of just snapping back is the thing can break. And of course, when that happens, you'll hear it again. And I'll do it right in front of the microphone. Again, that sound wave released is the release of energy, and notice now it's not all bendy and all that sort of stuff. In fact, I can stick the broken pieces back together, and it's, apart from the little splinters sticking up, it looks like it did before. And that's what happens at a fault. So you get that sudden breakage of something, energy is released, and that's what the earthquake is.
So, okay, that's the sort of natural movement of things.
Yes.
Is there I'm going to go out on a limb here. Can man create earthquakes? Fracking, perhaps?
Yeah, well, actually, yes. Fracking does actually contribute to seismicity. If you go out to places like Oklahoma or Kansas or Pennsylvania, in areas where they do fracking, there is what we call induced seismicity there, because what happens is fracking, you pump liquids into the ground to fracture weak rocks, usually a type of sedimentary rock called a shale. And the reason you do that is because there's hydrocarbons like oil and natural gas contained in it, and by breaking it up, you free it up, and then you can pump it out and use it as a fuel. So fracking actually stands for hydraulic fracturing.
Right.
But when you do that, you create other issues. So it's not so much the breaking up of it, is the pumping of fluids into the earth, into these rocks. And by adding fluids in there, it makes it easier for the rocks to move. Basically, by pumping liquid in there, you increase the pressure, the fluid pressure in the rocks. And that can be enough at sometimes to overcome the natural resistance of the rocks and have things move and all that. There's a very famous or infamous little demonstration that's done in intro structural geology classes called the beer can experiment, or the beer can demonstration, where you take you take a beer can and you put it on something like a wooden plank or something like that. And you lift up one end of the plank until the beer can starts to slide. It doesn't have to be a beer can. It could be a soda can or anything like that, but we're geologists, so they like beer. So you hold it up, and eventually it gets to some angle where it starts to slide. That makes perfect sense because, things will slide down an incline, and if it's lower, it won't do that. Well, what you do is you take an empty can, and of course, the way you properly do this is open the can and pour the stuff out because, you're doing an experiment. And what you want to do is then actually take the can, stick it in the freezer for a little while, get the air nice and cold. And you take it and you put it upside down with the opening at the bottom on top of your plank of wood. And then again, you lift up the end, it'll start to slide at a much lower angle. And the reason for that is the air inside the can, which was cold, is starting to warm up, and therefore it expands and therefore pushes a little bit between the can and the wood surface, or whatever the surface is made of. And so that's just enough to sort of lessen the contact between them and allowed it to slide at a lower angle. And that's exactly what's happening in hydraulic fracturing. Because you pump more fluids in there, you increase, we call it the pore fluid pressure. I can't speak right now. The pore fluid pressure in there, and it's basically then starts to separate the pieces from one another and therefore make it easier for things to slide.
So is that a temporary creation, or are they basically creating a new fault line in their region wherever they're doing the fracking?
You could be creating new ones because as this happens, especially with the fracturing, you're breaking new material. So you are, in a way, creating new faults and all that. The question of how permanent it is depends upon how much of the fluid sticks around. With fracking, you're supposed to pump the stuff back out.
Right.
But even if stuff is left in there, usually it'll migrate underground. And that's, of course, another reason why people are some people are not very happy with fracking, is because those fluids can make their way into groundwater and all that.
Right.
But so if that stuff moves away from there, you lessen the pressures, the pore fluid pressure. It's a tongue twister in that sort of rock, and therefore it becomes less likely the stuff would move again.
So we've learned that we can actually create into the rock. So to that point, let's say the San Andreas fault, is there the ability to impact that in a positive way by filling it in somehow, right? So that the plates, when they slam into each other, are cushioned somehow? Or am I just making stuff up here?
You don't want to actually make it more difficult for a fault to move or something. I mean, you may say, well, you don't want it to move, but the thing is, all those forces, they have to go somewhere. And if you don't, and actually what you would rather have is things move more, in a way more easily, because a little earthquake is fine.
Right. You want the energy to be released.
You want it. So if it can release the energy in like a million or something, really, really tiny little earthquakes.
Right.
That's fine, as opposed to letting everything sort of build up and letting it go all at once.
Yes. Okay.
But getting back to something like the San Andreas, there's really no way for us to sort of move big sections of rock and do that sort of engineering and all that. It takes a lot of energy, and those big earthquakes. I mean, there are smaller ones there, but remember, going up from a 2 to a 3 is 30 times more energy. Going a 3 to a 4, from a 2 to a 3 and then up to a 4, from the 2 to the 4 is 1,000 times more energy and all that sort of stuff. So things actually start to scale quite a bit.
Yeah.
And the natural resistance of the rocks to moving, because of the types of rocks they are, how far the faults sort of actually move, how far could they actually exist before they move. The surfaces, because the surfaces are not flat and perfectly smooth, you've got little, think of them as bumps on them. That's what's all sort of catching that stuff and preventing the motion in the first place. And all that has to be overcome. And if the stuff will move with less energy sort of built up and released, then you get a smaller earthquake. If it resists and kind of just builds up and builds up and builds up, then that's how you get a much bigger earthquake.
So to that point, are there certain markers that can serve as precursors to seismic activity, especially major seismic activity? And here's what I mean. When we have a hurricane that's coming up the northeast coast, or a nor'easter coming up the north, we have radar maps, and we have different model projections that can tell us, all right, we believe with some degree of certainty that it's going to hit here on some day and some time. Geologically, is there a marker that would say, hey, the San Andreas fault looks like there might be something going on there. There might be a major earthquake there in the next week or two. Or is it just so sudden that there's no planning that's available for it?
Right now, we cannot. I'll say it again. We cannot predict earthquakes. And when we say predict earthquakes, it's the scientific community has a very, very specific set of rules. In other words, you have to give a time frame. You have to say when, not vague, like in the next month. We're talking a prediction of like a time and date, a location as specific as possible, and also you want to talk about the size of the earthquake. You predict, well, that teeny little earthquake that I predict, that was the earthquake I predicted. And of course, the seismologists going, no, because you get literally millions of those size, magnitude ones. There are like 1 million earthquakes of those size globally every year.
Right.
So there's very specific criteria for claiming to predict an earthquake. And right now we cannot do that. What we can do is we can, people who are studying earthquake prediction, and there are people who are very interested in this, obviously, are looking to see, well, as you indicated, are there signs that seismic activity is going to happen? We can do things like measure the amount of strain across a section of a fault, like with our stick, with how much it bends. So how much is that bending? How much is that building up? We can measure things like electrical properties of the rocks, their resistivity or their conductivity. And we try to see, is there any correlation between any of that sort of stuff, and there's a whole bunch of other things we could do, with seismic activity, with an earthquake happening, because that would be what we want. That's what you're sort of alluding to. If we can look at that and say, oh, see the sudden increase, the sudden spike in this particular property, and that immediately following that, we had an earthquake. And if we see a particular ramp up in this, a particular increase, maybe there's a correlation to the magnitude of the earthquake, et cetera. We've never seen that. Could something like that exist? Well, maybe. Hopefully there is stuff like that, but we haven't been able to see that and use that as a prediction.
And that is the challenge, right? Because
it's a huge challenge.
That suddenness of an earthquake, right, makes it so much more dangerous, almost like a tornado where, you have an idea of where there might be tornadic activity, but until that funnel drops, you don't know where. And that's what makes them so deadly in a lot of cases, just like earthquakes.
And a big difference also with tornadoes and earthquakes is even when they, between tornadoes and earthquakes, or with tornadoes and hurricanes and the like, a big difference is when a tornado or hurricane occurs, we can see it and we can track it. And therefore we can say, oh, these areas, you're in the path of it.
Right.
So be on the lookout or head to a safe place and all that sort of stuff. With an earthquake, we can't do that. We can't say, an earthquake is come and get to,
it's reactive rather than proactive.
Correct.
Yeah.
What we can do is, and I know this doesn't help a lot of people, is we can look at certain areas, usually regions of a fault, like say this section of a fault, or a segment of a fault, and say, well, within the next 10 years, 20 years, 50 years, there is a probability of so much of a magnitude whatever, magnitude 4, magnitude 5 earthquake of happening in that time frame. I know for a lot of people that's not very helpful because you're not telling me when this is going to occur. You're not telling me exactly how big it is. It's like, no, but that's the best we can do right now.
Right.
And we do that because we can look to see how those portions of the faults have moved in the past. So geology has a history to it. So you go to areas and you can see what has happened in the past. We see the records of it. We can look at earthquakes and record the earthquakes that actually maybe have happened in certain areas and look at all those sort of factors there. And therefore we can say, oh, so we see earthquakes happening, magnitude 5 earthquakes in this section of, again, I'll say the San Andreas, happening with a period of, on average, of like 75 years or 120 years or something like that. So that allows us to say, okay, we should have in this time frame, this is the likelihood of this size earthquake sort of happening and all that. So we can sort of do that, and that does allow people to say, okay, is this a good place to be or not to be? And people can choose on their own, obviously, to do that. There are obviously lots of people living in Southern California, in Los Angeles, and San Francisco, which is not quite southern, but or going up to the Pacific Northwest.
And they do have building codes that
well, that's
future-proof or not earthquake-proof, but reflect that, right?
Yes, for the earthquake codes, they can then say, okay, this is the likelihood of these types of earthquakes, this size earthquake happening in this amount of time. Therefore, we want your building, we want to construct to be able to withstand that. If, on the other hand, you look at it and say, well, a magnitude 7 earthquake, we only see like a 1% chance of one happening in the next 3 centuries, then
maybe you roll the dice.
You roll the dice because, there's always trade-offs. So it's like, we can make a building much more likely to withstand strong earthquakes, but it's much more expensive to do that.
Right.
So you have all this cost-benefit analysis that you got to do, and that gets into the realm of just a public policy, which, of course, you want science to inform well.
That's right. So, okay, final question then for us here at home, right, in Paramus, New Jersey, when we talk about the probabilities, Is there a risk in the next, I don't know, you said 3 centuries of a 7 or an 8 or a 9, or are we just so below that
we're really below that? Sorry to interrupt. Yeah, is there the risk of seismic activity in this area? Of course there is. We knew that before this earthquake happened. Right. As you mentioned at the beginning of our conversation, New Jersey gets earthquakes. We get the state as a whole gets multiple earthquakes a year. Most of them are very, very small. We're talking magnitude 2s or less in general. Occasionally we get something stronger. The strongest recorded, actually, let me correct myself. It was not recorded, but the strongest earthquake that people experience that we have a record of was back in the 1700s, which we estimate to be about a 5.3.
Okay.
And the reason I say estimated is because, one, in order to get an earthquake magnitude, we need to record the earthquake, and seismographs were not invented until the late 1800s. So this is 100 years plus before that. And, of course, the Richter magnitude scale, which was the first of these magnitude scales, was not developed until the 1930s anyway. So we don't actually have it's an estimate. So we have records of eyewitness reports of what moved. We can go out in the field and see what moved and date it and do all the scientific work on it. And therefore we could say, well, this is characteristic of this size earthquake. So in those approaching 3 centuries since then, there have been 1, 2, maybe 3 total earthquakes of a 5 or bigger or something like that in New Jersey. Very low likelihood of anything very, very big around here.
Okay.
So I think we're pretty safe.
So there's plenty to worry about in our world, right? Earthquakes in New Jersey, probably not one of them.
I'd put it low down on the list.
All right, so sleep tight, my friends. Dr. Marton, thank you for an incredible conversation on a topic that I'm sure a lot of people just don't have a lot of knowledge about, since at least they went to high school maybe or took a college class. So thanks a lot.
My pleasure.
So that wraps up another episode of the official podcast of Bergen Community College. Never mind the noise and the chatter. We are here for intelligent, fact-based conversation here on Bergen Banter, and we'll see you down the road.